Okay, good morning, everyone. Welcome back. Please, I hope you can hear me. Okay, I think, can you hear me? Are we good? Okay, awesome. Perfect. Okay, so it's time. So let's get on to work. But before we start, as usual, do you have any questions for me? Any issues with homework, any problems, any technical issues, any comments? Do you have any comments or anything? Okay. So if there are no comments or problems, then let's get on to today's session, right? So on Wednesday, we wrapped up the L'Hopital's rule, right? The indeterminate forms and L'Hopital's rule. So today we are continuing on chapter 4.5, right? So let me share my screen. I'm sharing my desktop. If you can't see, do let me know, right? So you're on 4.5, curve sketching. Let me see. Okay, so for curve sketching, it's still under applications of differentiation, right? It's still under application of differentiation. So summary of curve sketching. Now for this session, the summary, we are just going to look at some steps you have to consider to be able to get like some important features of a graph, right? So when we want to sketch a function, what are some of the important features we have to look at? So that's what we're going to walk through, right? So these are just guidelines, right, for sketching a curve. Now, we start by saying that it's just a checklist, right, which is intended to guide you to sketch. Now, sometimes for some functions, some of the items on this list may be relevant to some other functions, right, not to all functions, right? So it's function dependent. So it's not all functions that will have all of these features, right, that we are going to look at, right? So just note that. But this is just a general list of set of things you have to look at when you are going to graph or sketch a function. So now the first thing that you have to focus on is the domain, right? That's the first thing. So you have to determine where the function is defined, right? That's the first step. The next step is you try and find your intercepts. Now here, the thing is, if the thing is too complicated and you can't solve, then you probably have to, you can probably omit this, right? So you can omit this if the equation is difficult to solve. Now, how do you find the intercepts? So for intercepts, you're looking at two kinds of intercepts, right? You're looking at the s-intercept and then the y-intercept, right? So for s-intercept, how we solve it is we set x, for the y-intercept, we set x equal to 0, right? And solve for the function value at that 0. Now for the x-intercept, on the other hand, you set the y or the function equal to 0 and then solve for the x values, right? So those are the intercepts. Now, the next thing we are going to talk about is symmetry. Now, for symmetry, we start with the first kind of symmetry, which is known as an even function, right? Now, we say an even function is symmetric to the y-axis. It's symmetric about the y-axis. Now, what do we mean by that? Now, let me just show you. You all remember the function x squared, right? The function x squared, kind of like a smiley face kind of thing, like so. This is why you call it x squared. Now, this function is an example of an even function. Or in terms of symmetry, it's a function which is symmetric about the y-axis. Now, why is this symmetric about the y-axis? All that we are saying is, if you have half of the graph, right? So if I have, say, from 0 to infinity, then technically I can just reflect that using the y-axis and get the other half, right? So that's why we concern ourselves with symmetry. So we say a function of this form, right, is what's symmetric about the y-axis. Now, when you're doing this computation-wise, how to decide whether a function is symmetric? You first have to note that for every x in the domain of D, negative x will also be in the domain of D. And when you plug the negative x in the function, you're going to get the original function. So let me just let's look at quickly how we're going to look at this. So for this example that I just wrote down, for y equal to s squared, in function notation, we have f of x equal to s squared, right? So if I plug in negative x for every x in the domain, its negative x will just be what? Negative x all squared. So I'm just plugging negative x for x in this function up here. So you are going to get what? Negative x all squared. Now, what is negative x all squared? Well, negative x all squared is just s squared, right? but s squared is the same as the function that we started with. So when you plug in negative x, you still get back what? F of x. So with this test, with this quick test, we can say, okay, yes, this function is what? It's an even function. Hence, it's symmetric about the what? The y-axis, right? The deal with symmetry is, as I told you earlier on, it cuts our work in half. So suppose you're trying to sketch a curve, and we know it's symmetric about the y-axis, then technically we can just focus on one side, right? And then when we are done, right, say for one side, so from say the 0 to infinity part, and then when we are done, we just reflect that part that we obtained in the y-axis and then get the other half. So that's how come symmetry helps us when we are sketching, right? Yeah, so it can help us to cut our work in half. Please, any questions so far? Are you okay on this? Anybody needs time on this slide? Now, as you notice, this is just I, right? The I and the symmetry. We have other kinds of symmetry. I'll talk more about that, but this now going to emphasize on how the symmetric about the y. So this is just examples, right? So you see this graph. When you look at just this side, you can see that if you reflect it in the y-axis, you get this side, right? That's symmetric about the y-axis, right? So that's it. Now, examples of subfunctions are y equal to s squared, which I showed you earlier on, y equal to s to the power 4, y equal to absolute value of x, and y equal to cosine of x. For each of these, their graphs will be such that when you reflect the 0 to infinity part on the y-axis, you get the other half, the corresponding half. Or testing this algebraically, right? For the y equal to s squared, I did that on the previous slide. For the y equal to s to the power 4, this in function notation, we have f of x equal to this. So if you plug in negative x, you have negative x to the power 4, which is still s to the power 4, which is the original function. So I know that, okay, yes, this is what? An even function. So it's symmetric about the y-axis. The same with the absolute value of x, right? So for y equal to absolute value of x, which is the function notation is f of x. If you plug in negative x here too, you're going to get absolute value of negative x. And that's just going to be what? It's the same as what? Absolute value of x, which is the original function that we started with. So we know that this is what? An even function. Please, I hope you get this idea. Now, the same holds with cosine, right? So for cosine, let me asterisk these ones. For y equal to cosine of x, right? In function notation, the representation is f of x. So if you look at f of negative x, you're just going to have cosine of negative x. And cosine of negative x is cosine of x. So that's the same as what? The original f of x, right? So when you plug in negative s, it doesn't change the function form. So that is what? An even function. So it's symmetric about the what? The y-axis. So that's it. Now, as I was saying, there are other kinds of symmetry. The next thing you're going to look at is symmetric about the origin. And that one, those functions are called odd functions, right? So when we have an odd function, it's symmetric about the origin. Now, for that one, a quick algebraic test will be just plug in negative x. When you plug in negative x, you are going to end up with the negative of the original function. The negative of the original function, right? So there's a quick way to see that it's an odd function. Now, what do you mean by symmetric about the origin? Well, once more, just as we had it for the symmetric about the y-axis, for symmetric about the origin, when you rotate one half of the graph, say from the 0, if you take from 0 to infinity, and you rotate it 180 degrees, it will give you the other half, right? So if you rotate it 180 degrees, it will give you the other half. So for this one, let me see. So it's kind of like so, right? So if you have this piece and you rotate it 180 degrees, right? You rotate it 180 degrees, you get a corresponding half, which is here. So this also cuts our work in half. We can just focus on graphing the positive part, from 0 to infinity, and then we can get the corresponding negative part, right? Please, are you okay with this? Any questions? Right, so let me get a good graph here. Give me a sec. Okay, so keep and then drop. Erase. Okay. and then shift. Okay, yeah, so that's the point on this one, right? So rotate it 180 degrees and you get a corresponding half. Please, any questions here? Are you okay? Right, so rotate everything. Yeah, so that's symmetric about the origin, right? Now, let's look at examples on symmetric about the origin. Well, a popular example is y equal to x. Well, in function notation, we have f of x equal to this. So if you do the f of negative x, right, it will just be negative x, which is the negative of f of x, right? Because f of x is x, and this is negative x, so it's the negative of f of x. Now, immediately with this test, we can say that this is an odd function. So that means it's what? It's symmetric about the origin. And for this now, because the graph is a quick one, let me show you how the graph will look like. It will look like this. This is the identity function, right? It's y equal to x. Right? So when you rotate this 180 degrees, you get a corresponding. So if you rotate from 0 to infinity, right? If you rotate this side, this half, 180 degrees, you get a corresponding second part, right? And then the same with the y equal to s to the cube, right? So if you have y equal to s cube, in function notation, that's f of s equal to this. And if you do f of negative x, you're going to get negative s all cube. And negative x all cube is negative s cube, which is the same as the negative of the original function. So with this quick test, with this quick algebraic test, we know that this is an odd function, hence it's symmetric about the origin. Please, I hope you're okay. Any questions on this? Okay. Now let's look at the third kind of symmetry. But for this one, you're not responsible here, but I'll just talk about it. You're not responsible for it in this class, but it's on this slide, so I'll talk about it. Now, the last one we're going to look at is something we call a periodic function, a periodic function. Now, what is a periodic function? Well, a function f of, if we plug in x plus p, and we still get back the f of x for all x in the domain, where p is a positive constant, then f is called a periodic function. Well, in other words, it reoccurs at every period p. So what we mean by that is, let's say you have one piece of the function. Say you cut one piece of the function. Now, if you cut one piece of the function and add p to every part of the piece that you cut, then you get the next piece, right? You get the next piece. So it's periodic, right? For every period, it repeats, right? So this is just a very good graph to see what is happening here. So for this one, you see that if we are to slice this function on this side, right, then this piece is the same as that piece, which is the same as that piece, and so on and so forth, to the right and to the left. So more or less, when you are graphing a curve like this, you can just focus on this side and then just repeat it for every p, and then you have the function, right? A very good example of this is sine of x, right? Sine has a period of 2 pi, and we have tangent too. Tangent has a period of pi, right? Yeah, so that's periodicity. But as I said, you won't get any questions on this on the homework or on an exam. Yeah, but I'm just for information purposes. Please, any questions here? Anybody needs time? Okay, now let's move on to another thing, another important feature. This one is the asymptotes, right? Asymptotes. Now, in previous lessons, we've talked about the horizontal asymptote and the vertical asymptote, right? So we repeat these here. For horizontal asymptote, we need to look at limits at infinity. So we are looking at the limit as it approaches infinity of the function. If it's equal to L, which is a constant, right? Then we say y equal to that L is a horizontal asymptote. On the other hand, if the limit as it approaches negative infinity, or the function is also L, right? These two L's could be different, right? In this case, they use the same L, but you could have two. It's possible to get two horizontal asymptotes, right? So in either case, if this limit at infinity, whether negative infinity or positive infinity, is giving you L, then remember it's a horizontal line, so you need a y equal to, right? So y equal to that L is a horizontal asymptote. Please, are you okay so far? Any questions? Well, one other thing you have to note here is when you sort to find a horizontal asymptote, sometimes you may not get a constant, but that information is still not useless. It's still useful. Suppose you're trying to find a horizontal asymptote, and so you are taking limit at infinity, but then you end up with an infinite limit, which is either plus or minus infinity. If you get this information, it's not totally useless. even though you didn't get a horizontal asymptote, you can still know that, oh, at the ends of the function, right? Say you did this and you got infinity, and you did this, you took the limit as you approach negative infinity, and you got, say, negative infinity. So suppose you are trying to find horizontal asymptote, but these were the results you got. Then it's still not useless, because you know that, oh, as the x approaches infinity, I expect the graph to be moving up, right? On the left-hand side, you say, okay, because this one, as you approach negative infinity, the graph is expected to go down. So at least, even though it doesn't give you horizontal asymptote, but it gives you information about the end behavior of the function. Please, are you okay on this, on the horizontal asymptotes? Any questions? Now, the next other kind of asymptote you're going to look at is vertical asymptotes. So for vertical asymptotes, right, that one is a vertical line. So it's x equal to a, right? Now, how do we know that x equal to a is a vertical asymptote? Well, for that one, either you're taking one-sided limit as you approach a, so either from the right or from the left of a, and you are getting an infinite limit. So the result is either positive infinity or negative infinity. Then that means that what? Your x equal to a is a vertical asymptote, right? Now, the way to find vertical asymptote is, remember that if it's a rational function, a polynomial of a polynomial, we usually set the denominator equal to 0 and get the candidates, right? And then test their one-sided limits. If it turns out to be an infinite limit, then x equal to that number is a what? It's a vertical asymptote. So we looked at this way back. So this is just a reminder. Now, for other functions, it may be different. For example, if you are looking at 0 from the right of ln of x, for ln of s, this is negative infinity. You don't have a denominator to set it equal to 0, but you know that for this structure, the limit as you approach 0 of this function is what? Oh no, is 1 here, and it goes down. So there's y equal to ln of x, right? Yeah, so you know that the limit as you approach 0 for ln of x is what? Is going to approach negative infinity. Yeah, so that's what this is about. Please, any questions on the vertical asymptotes? Now, the last kind of asymptote, which you'll not be responsible for, but which I have to talk about, is a slant asymptote. As you can see, there are no notes here, right? There are no notes. But for slant asymptotes, you get it if you have a rational function. So rational function. So this is about slant asymptote, right? So we have a rational function. So a polynomial of a polynomial. And then you notice that the degree, say the degree of here of the numerator is yeah, let me do the degree of the denominator first. The degree of the denominator is n, and then the degree of the numerator is n plus 1. So whenever you have the degree of the numerator being 1 more than the degree of the denominator, then you're going to get a slant asymptote, which will be obtained by long division. But from your work that you got for this section, you are not going to be tested on this, right? So not on a homework, not on an exam. So you can more or less ignore this for now. Yeah, but that's what is going to happen. If you have a rational function and the degree of the numerator is 1 more than the degree of the denominator, then you get a you get a slant asymptote, right? Yeah. Now, the step E says find the intervals of increase or decrease. So for this one, you're going to perform the ID test, which we talked about, right, in previous lessons. Please, any questions so far? Are you okay? Okay. Now, the F is the local maximum and minimum values, right? So we do ID test, and then we do local maximum and minimum values, right? And for local maximum and minimum values, it follows directly after the ID test, right? So yeah, that's it on this one. Now, can anyone guess what's going to follow? If you do ID test, you do local maximum and minimum values. Can you guess what's going to follow? What's the next step? Anybody? Take a wild guess. What do you think? ID test, local maximum, minimum. Close, absolute mass or min. Close, try again. ID test, local mass or min. What follows? You saw something similar on your quiz yesterday. Yes, kind of, inflection point. But then what comes before inflection point? Perfect. Concavity. Awesome. So ID test, first derivative test, concavity, inflection point, right? So that's definitely the next step. So you look at the concavity and points of inflection. And for that one, you need a second derivative. And then you perform that test. Now, after you get all this information, the last thing is to sketch your curve. So these are the guidelines. Please, any questions on any of the guidelines? Is there anything you don't understand that you want me to go over? Okay, so if there are no questions, I think the fun thing will be to try the example. So as you know, this is a lot. You have a lot of things to go through, to go over. So we are just going to do one example, right? So after we get everything, we just pass the lines through them, right? So I think an example would be a good way to see this. So our example is this, right? So let me do, the solution is on the PowerPoint, but I don't want to slide through, right? So let's do this on the whiteboard. So 2s squared over s squared. So example is y equal to, in function, we have this. Please, I'm sharing the whiteboard now. If you see, do let me know. S squared minus 1. So this is our function. Okay, so let's walk through the guidelines. So A, need a domain. Right? So for the domain, because this is a rational function, we need to make sure that the denominator is not 0. Because if the denominator is 0, then the whole thing is undefined. Right? So what we're going to do is set the denominator equal to 0. And right, I hope you recall some of these calculations. You probably undertook these in like 126 and so on. Right, so let's find the domain. So for this, if you are solving this, you have s squared equal to 1, which means x is equal to what? S is equal to, sorry, plus or minus 1, right? So interval notation, your domain will be from negative infinity to negative 1, and then in your negative 1 to 1, and then union 1 to infinity. Please, are you okay on this? Okay. Now the B is the intercepts. Now for this, please help me out here. Can anyone help me with any of them, like either S or Y intercepts? Please try your hands and let's see. For Y-intercept, we set S equal to 0. For S-intercept, we set Y equal to 0, and so on. So please help me out. Anyone you get, that's fine by me. So Y-intercept, and then X-intercept. I think, yeah, and then X-intercept. Anybody? Hope you've not forgotten the computation. So for Y-intercept, set S equal to 0. And then you solve for the Y value. For S-intercept, set Y equal to 0, solve for the X value. So what do you get? Anybody? Okay, yes, 0. Yeah, perfect, thank you. Yeah, okay, very good. Thank you for your response. So let's do it together. So for Y-intercept, we set X equal to 0. So for Y. Right, so we have Y equal to this. So if you set S equal to 0, you have Y equal to 2 times 0 squared. And then over 0 squared minus 1. So that would just be 0 over negative 1, which is 0. So we can say the Y-intercept is just 0, 0. The fact that we got 0, 0 should tell us that we should get 0, 0 as an S-intercept, right? But let's just do the math for this. So for this one, set Y equal to 0 and solve for X. Right, so we're going to have 0 equal to 2S squared over S squared minus 1. Now, the thing is, when you get here, for a quotient to be 0, that means the numerator is equal to 0. And whatever solution that you get, it should not be such that it makes the whole thing undefined, right? So 0 equal to 2s squared over s squared minus 1 implies 2s squared equal to 0. But the solution we get should not make this undefined, right? That means we can't get negative 1 or 1, right? Because those are even not part of the domain in the first place. So when you get here, you can divide both sides by 2, and you get s squared equal to 0. Solving this, you get s equal to 0. So you see, so that's the only X-intercept. So 0, 0. Please, I hope you get this. Okay, any questions on the intercepts? Okay. Anybody needs time here? Okay. Then let's move on to C. The C is symmetry. Symmetry. So for symmetry, a quick check will be to try it algebraically, right? So the function is, this one, let me use function notation. It's f of x is 2s squared over s squared minus 1. So if you're trying to test for symmetry, right, you know the domain is from negative infinity to negative 1. And then, you know, negative 1 to 1, and then, you know, 1 to infinity. Let me get some more. Negative infinity, negative 1, negative 1 to 1, 1 to infinity. Okay, so we are here. So all that we have to try is just test the negative x here and see what you're going to get. As long as this x, negative x is part of the domain, let's see what's going to happen. So you have 2 negative x all squared over negative x all squared minus 1. And that's equal to what? So negative x all squared, that's 2s squared. And then all over what? Negative s all squared is s squared minus 1. Now you notice that this function is the same as the original function. So can you please help me out? What kind of function is this? Is this an even function or an odd function? What do you say? Perfect. Thank you, Jessica. So it's an even function, right? It's an even function. Now, because it's an even function, we know it's what? It's symmetric about the y-axis, right? It's symmetric about the y-axis. That means we can, if we want, we can cut our work in half. Just focus on only the positive part of the function. So 0 to infinity. Sketch that part, and then we can just reflect that part in as then we get the other half, right? Hence symmetric about as. Even though we know this, we are still going to do everything for this function, right? But this is just something to note you could have done, right? Okay, please, any questions on symmetry? Okay, now if there are no questions on symmetry, let's move on to the next step, which is D. For D, we are going to look at asymptotes. Right, asymptotes. Now, asymptotes. So for asymptotes, you are going to look at horizontal and then vertical. Well, for one, the degree of the numerator here is equal to the degree here, the degree of the denominator, right? So this one won't have a slant asymptote. But as I said, you won't have a question on slant asymptote here. From the content that I saw, you have none of those on the homework, or yeah, none of those on the homework and in the content. So I'm not going to test you on that, right? So for this one, we just check for the two. You're looking at horizontal asymptotes. Asymptotes. Right. Now for horizontal asymptote, we need to look at what? Limit at infinity. Right. So limit as s approaches negative infinity and limit as s approaches infinity. But the thing is, this expression that we have here, the function that we have here, is a rational function. And if you remember from chapter 2, we learned that for rational functions, if the limit exists, I'm not saying if the limit is infinite, if the limit exists, then both the negative infinity and the positive infinity will give you the same result, right? So that means for that one, you don't have to do for the two, right? So let's do for limit as s approaches infinity of the function. So we have 2s squared over s squared minus 1. So for this one, can anyone help me with this limit? Do you remember how to get this? What would be the answer to this one? Anybody? What will be this limit? Okay, I have 2. Do I have a second or a different answer? Thank you, Hunter. Yeah, I have a second or 2. Thank you, Sage. Yeah, that's correct. Now, the degree of the numerator here is 2. Right? The degree of the numerator is 2. And then the degree of the denominator is also 2. Now, because the degrees match, that means that the result will be what? A quotient of the leading coefficients. So that will be 2 over 1, which is 2. Right? And then we are done. Or you could have done the long approach. So divide by the greatest power of x in the denominator. So that will be s squared. divided by s squared over s squared. Now, at this point, you have a lot of options. You could have even used L'Hopital if you want. You can even use L'Hopital. So you're not short of options. You have a lot of options. So here, if they cancel out, you have 2 over 1 minus 1 over squared. And as s approaches infinity, this 1 over s squared here will approach 0, right? So we still get 2 over 1, which is 2, right? But as I also said, the limit as s approaches negative infinity for a rational function, if the limit exists, will be the same thing. So for limit as s approaches negative infinity of s squared, 2s squared minus 2s squared over s squared minus 1, you're still getting 2. Now, for horizontal asymptote, you have to be cautious because, as I said, sometimes the answer you get for the limit as you approach infinity may be different from the answer that you get for the limit as s approaches negative infinity. But then the case is for rational functions, if the limits are this, if the limit exists, then they'll be the same. So just be careful of that. So always do it for the 2 and see. Please, any questions so far? Anybody need time here? Okay, now let's make the conclusion, right? So for the limit at infinity to be 2, the conclusion is, can say y equal to 2 is a horizontal asymptote. Okay, so we have the horizontal. Now let's check for the vertical asymptote. Vertical asymptote. Now for vertical asymptotes, if it's a rational function like we have here, right? So we have fx equal to 2s squared over s squared minus 1. You remember that I said that if it's a rational function, then the candidate for horizontal asymptote is when we set x, the denominator equal to 0. We set the denominator equal to 0. So we just start by setting equal to 0, right? So you still end up with s equal to plus or minus 1, right? So either s equal to negative 1 or s equal to 61, right? The thing is, if the function is already simplified, if it's in lowest terms, then this is your answer. X equal to negative 1 and s equal to 1 will be your answer, right? But as I said, with calculus, you have to check these limits with what and see if you get limit at infinity, right? Sorry, yeah, you get an infinite limit. Sorry, you get an infinite limit. So let's try and test for these, even though we know that this was in lowest terms and then this was going to give us this, right? Let's test and see. So let's try limit as s approaches. We need one side, so negative 1, say from the right of the function. Now, another thing, because you are going to graph it, you do for the 2 sides. So we do for the right and then from the left. So that when we are graphing, we know, okay, from the right, you are approaching infinity, maybe from the left, you're approaching negative infinity, or the other way around, right? Or the 2 are both approaching infinity from both sides. You see, so you have to do it for the 2-sided for each of the candidates. So let's test for negative 1 from the right. So you have 2s squared over s squared minus 1. Now, let's try and evaluate this limit. Now, for this limit, if you're trying to evaluate this, negative 1 in the top, so we try by first plugging in. So negative 1 on the top will be 2, negative 1 squared is 1, right? 2 times 1 is 2. Now, for the denominator, well, you can clearly see that when we got the negative 1 by solving for the denominator equal to 0. So obviously, when you plug in negative 1 here, you get 0 down there. But then what do you see? This is what? A non-zero number. A non-zero number over 0. And it's one-sided. So can you guess what the answer will be? The answer will be either what? Do you remember this statement? Yeah, it's a non-zero number over 0. So what do we expect the answer to be? It's either going to be, give me the 2 possible answers. Non-zero number over 0. What are the 2 possible answers? Anybody? Close, non-zero, close. Come again, Mega. Try again. Non-zero number over 0. We did this in chapter 2, if you recall. And it comes up sometimes. DNE, close, very close. It's one-sided. So it's going to be one of them. Non-zero number over 0. Thank you, Katrina. Yeah, it's either infinity or, yeah, it's infinity or negative infinity, right? Non-zero number over zero, the answer for one-sided limit of non-zero number over zero, you're either going to get infinity or negative infinity. But since we're trying to have this, let's get the precise answer for this, right? Answer to this one. So let's see. Okay, this one is giving us the numerator is approaching 2, the denominator is approaching 0. But the question is, looking at the denominator, which part of 0 is it approaching from? Is it approaching 0 from the right? In other words, is it like something like 0.00001, or is it approaching 0 from the left? Or something like a negative 0.00001 of some sort, right? So just track the point here is -1, and you're approaching from the right, so from this side. So from the right here, the values to the right of -1, right? So you have to be careful. So it's kind of like -0.9999 of some sort, right? So if you plug the -0.9999 kind of number here, if you try and analyze where this is approaching from, the -0.9999 here will be what? A positive 0.9999. It will still be less than what? The 1. So that means it's approaching 0 from the left. So the denominator is something like a negative 0.0001 of some sort. Right. So for this one, the numerator is still approaching 2. The denominator is approaching a negative 0.000 of some sort. Can anyone tell me what the answer to this is? What is this? Anybody? What do you think the answer to this is? Perfect. Thank you, Robert. Yeah. So it's negative infinity. Thank you. So that limit to be negative infinity. So from the right of -1 is negative infinity. Now let's try it also from the left so that we see it for that side too. From the left of -1 of 2s squared. So for this one, right? Still, when you plug -1 in here, you're going to get the numerator to be 2, and then the denominator will be 0. But let's check from which direction of 0 is it approaching from? Is it approaching 0 from the left or from the right? So track -1 to the left of -1 is from this direction. So for that one, you're looking at numbers like -1.000 or some sort, right? So that one, if you plug it in here, you're getting a positive 1.0001 of some sort. So it will be a little bit bigger than 1. So that means that when you do the subtraction, this one is approaching 0 from the right, right? So that means this over this will give us what? Infinity. So we've done it for the -1. Please, do you have any questions on this? Is there any part you don't understand that you want me to explain again? Okay, so if there are no questions, then let's move on to the next one. So for the next part, we had 2 numbers here, right? We had either -1 or +1. So let's also do it for x approaching 1 from the right, of the function. So 2x over s squared is 2s squared over s squared minus 1. Okay. Now, just as we had for the previous cases, right? If you plug 1 in here, you're getting 2 up there, and then you have 0 down here. But the question is it approaching 0 from the right or from the left? So locate 1. Now, from the right of 1, what numbers are there? It's something like 1.00001 of some sort. Now, if you plug it in here, you're getting what? Something bigger than 1. So that means it's approaching 0 from the right. So that 2 over this will give us what? It's similar to this one. So it's infinity up here. Please, I hope you're okay. Any questions up to this point? Anybody needs more time on this slide? Okay. Now, let's do it for the last limit, right? From the right. So limit as x approaches 1. It is from the left or from the left. So that's 1 from the left, and then 2s squared over s squared minus 1, right? So still, if you plug it in here, the 1 in here, you get 2 on the numerator, and then the numerator is 0. But is it approaching 0 from the left or from the right? In other words, is this something like a positive 0.001? Is it taking on numbers like that? Or is it taking on numbers like negative 0.001? Well, if you track 1 here, from the left of 1, you have values like 0.999. It's taking on values like 0.999, right? And then 0.999 squared will still be less than this one. So that means it's approaching 0 from the left. So it's taking on values like this. And 2 over negative of that is just going to be odd. The limits are approaching negative infinity. Right. So whenever you are graphing and we get to these points, we know what to do there. Right. But then that was not the main thing we sought after. We are trying to find vertical asymptotes. But now that we've been able to see that these limits are infinite limits, we can conclude that what s equal to -1 and s equal to what 1 are vertical asymptotes. Okay, so that's it on that one. Please, any questions so far on asymptotes? Okay. Now, let's get on to the intervals of increase or decrease. So that'll be E. Right, so where the function is increasing or increasing. Now, to perform the ID test, what do you need? What do you need? Can anyone help me with that? What do you need to perform ID test? What do you need? Perfect. We need f prime. Thank you, Megan. We need f prime. So if you have f of x equal to 2s squared over s squared minus 1, you need f prime. Well, this one is going to take space. So let me do this on the next slide, right? But let me know if you need more time here. I'll do this on the next slide. It won't fit here. Anybody needs more time here? Okay. So for f of x equal to 2s squared over s squared minus 1, f prime of x will just be attach the differentiation operator to this function. You have d over dx of 2s squared over s squared minus 1, right? So what rule are we going to use here? Can anyone please help us here? What rule? What rule are we using here? How do we get this derivative? What rule? What rule do we use? Come on, what rule? What do you think? Yeah, quotient rule. Thank you, quotient rule. So quotient rule, low, d high, the derivative of 2s squared is what? Is 4s minus high, 2s squared, d low, 2x, all over square of what is below. All over the square of what is below. So that'll be s squared minus 1 all squared. Right, so we have it. And then we try and simplify. Right, so you distribute the 4x through 4x times s squared, that'll be 4s cubed. And then 4x times -1, that'll be minus 4x. And then you distribute this, you multiply this, right? So you get minus 4s cubed. And then all over, you have s squared minus 1 all squared. Okay, so what are we getting? When you simplify, the 4s cubes will cancel out. So that'll leave us with f prime, which is equal to -4x over s squared minus 1 all squared. Right, so we have the f prime. Now, after getting the f prime, what do? We try and find the critical points, right? So let's find the critical numbers. Right, so for the critical numbers, we need to check for 2 conditions. We need to check for f prime of s equal to dne, right? And then f prime of x equal to 0, right? Those are the 2 conditions you have to check. Now, for the f prime of s equal to dne, the question is there any x which makes the f prime undefined, but which was part of the domain of f? Well, when you look at this f prime, you can see that -1 and 1 will make the denominator 0, so it will make everything undefined. But in this case, -1 and 1 cannot be critical numbers because they were not part of the original domain of f. Right? Don't forget that the domain of f, we stated that earlier on, but let me write it here for convenience. It's negative infinity to -1, union -1 to 1, and then union what? 1 to infinity. Right? So -1 and 1 are not part of the domain, so they cannot be critical numbers. So this one is no critical number for this condition. Now for the second condition, we just set the f prime of x equal to 0. So we have this all squared equal to 0. Now for a quotient to be 0, right? And then for all defined values of x, we need the numerator to be 0. And the solution is x equal to 0. 0 is part of the domain of f, so that's the solution. We have it. Right, so that's the only critical number. Right, this is the only critical number. This is the only critical number. Please, are you good so far? Any questions? Anybody needs time here? More time, that is. Okay, so now, after getting the critical numbers, right, what do? We partition the domain of f using the critical numbers, right? In this case, we just got 1, right? We just got s equal to 0. So we partition the domain of f. Now, the thing you have to be cautious of is, for this function, the domain is already partitioned. It has excluded -1 and 1. So we partition the domain of f. So the domain of f is from -infinity to -1. So for -1, you can do a point tool here so that you know that that's not part. And then we split the domain and at the critical point, and then 1, and then infinity. Right? So the domain was this. The domain was already partitioned. This is the domain, how it looks like on a number line. And then we partition the domain using the critical point. So that's 0. So that'll give us what? 1, 2, 3, 4, 4 intervals. So we do our table. We have intervals. That's from -infinity to -1. -infinity to -1. And you have -1 to 0. And we have from 0 to 1. And we have from 1 to infinity. Right? And so with this one, we need to check the sign for f prime, right? So you look at f prime, it's -4x over this, right? So -4, let me write the whole thing together, right? So I have f prime over x is -4x over s squared minus 1 all squared. And then after getting the sign for f prime, I can tell what is happening with f, whether it's increasing or decreasing, right? Okay. Now, for this function, right, just pick a number in this interval. The thing is, the denominator is squared, so it's always positive. So you don't really have to worry so much about the denominator. The focus should be on the numerator, right? So pick a number here, or if you want, you can put it in the entire thing, right? But I'm just trying to save some time. So let's pick a number here, say -2. -4 times -2 is a positive number, right? So that's it. Pick a number here, say -half. -half times 4 is also positive, right? And then pick a number here, say half. Half times -4 is negative. Pick a number, 2. 2 times -4 is also negative. Now for this side, because the f prime is positive, I know the function is what? It's increasing. The same with this. No, this one is different. This one is decreasing because it's negative. And then this one is also decreasing. Right, so the function is increasing on this interval, on these 2 intervals, and it's decreasing on these other 2. So we are done with the ID test. Please, any questions on this? Okay, so that's E. Now let's move on to F. If you don't need more time here, I'll need to move on to the next slide. Okay, so F. For F, we are looking at local maximum or minimum values. Now, for that one, what do? We just replicate the partition that you created earlier on, right? From -infinity to infinity, we had -1 is excluded from the domain, 1 is also excluded, and we have 0 as a critical point. And right here, it was increasing. So I have increasing, and decreasing. So the thing is, one thing, please note that the -1 and 1 are not parts. So even if we had a case like this at -1, it won't be a local extreme value because -1 is not part of the domain. So note that, right? So that's why it's important you do that point tool there so that you always you are always alert that it's not part. I think I'll end with the local extreme values because it's almost time. So now looking at this, I know that 0 is part of the domain, right? And at 0, I see a switch from increasing to decreasing. So the function is behaving like so. So what do you think is happening at 0? What local extreme value is happening there? Is it a maximum or a minimum? Perfect, perfect. So local maximum occurs at s equal to 0, and the local maximum value is the function evaluated at 0. And if you remember, this is just 2s squared, so that'll be 2 squared over 0 squared minus 1, which is 0. So this is the local maximum value. Okay, so it's 11:50, and that's all time will allow for today, right? So please note that you have your exam coming up next week. If you have any issues, feel free to set up an office hours or something. I can help you work more questions, or if you don't understand anything on the study guide too, feel free to reach out. And so we'll continue with this question on Monday when we meet. Have a nice weekend. All the best. You are welcome.